So, types of radioactivity. So, Curie focused her work on discovering different radioactive elements. Ernest Rutherford, whom I know you've heard of before, because we talked about him in 1A. Rutherford and others focused on trying to figure out what radioactivity was, its properties, where it came from, etc. So the nuclei of radioactive elements are unstable, and they will just spontaneously decompose. And when they do that, they emit small pieces of the nucleus to increase the stability of the nucleus. There are several categories of natural radioactivity, and these include alpha rays, alpha decay, beta decay, gamma ray emission, positron emission, and electron capture. So let's take a quick review of nuclear symbols that you learned in Chem 1A, because we need these again. So this is a nuclear symbol. The large letter here is the chemical symbol, the element symbol from the periodic table. A, as a subscript on the left, is the mass number. Remember that the mass number is the sum of protons and neutrons in the nucleus. That's also going to be the approximate mass of that atom in atomic mass units, because protons and neutrons are very close to 1 atomic mass units, and electrons are just crazy small. The other number here in the bottom is the atomic number. That's the number on the periodic table, with the element symbol, the number of protons in the nucleus. So if we want to know how many neutrons something has, you can take the mass number and subtract the atomic number. And I used to get confused about which one was on top and which one was on bottom. And then I realized it's set up so that you can just subtract it. A minus Z gives you N. So most elements have several different isotopes. There are elements that have 2 isotopes or 4 isotopes, and it's not predictable from the periodic table. We often refer to a particular isotope of an element as a nuclide. We can represent isotopes with the nuclear symbol. We can also represent them by the element name or symbol, followed by the mass number. So different ways to represent carbon-14. That's the nuclear symbol. We can call this C14, or we could call this carbon-14. The 6 is really not that important. It doesn't have to be in this name, because we find carbon on the periodic table and we know what the mass number is, the atomic number. We can also represent the main subatomic particles using nuclear symbols. So the proton is the symbol lowercase p. Its mass number is 1, and its number of protons is 1. Right? So how many neutrons does a proton have? 0. How many electrons does a proton have? 0. It's just a proton. A neutron has a symbol lowercase n. Its mass number is 1 because there's 1 neutron, and its atomic number is 0 because there are 0 protons. And then the electron is a lowercase e, mass number 0. That makes sense, it has no protons or neutrons. Its atomic number is -1, and we'll see where that comes from in a minute. So alpha decay, we have an unstable nucleus that emits an alpha particle. An alpha particle has this symbol here. It is the same as a helium nucleus. It's the helium nucleus without the electrons. Okay, so 2 protons, 2 neutrons, that's going to be emitted. And so We do need to remember that an alpha particle is the same as a helium nucleus. So we can write nuclear equations, like we write chemical equations, that represent the nuclear processes. Here we have some extra information. We have mass numbers and atomic numbers for everything in the equation. And here we are not concerned about having the same number of atoms of each element on each side. That's actually not going to happen. Because here we are changing elements into other elements. Okay? So all of those things we learned in 1A, it was all this and this and this in a chemical process, right? So this is the not a chemical process, this is the nuclear process where funny things happen. So here what we're trying to balance is the atomic numbers and the mass numbers on both sides. So the sum of the mass numbers on both sides of the arrow has to be equal. The sum of the atomic numbers has to be equal. But we see that elements will often change into different elements. So in this example, we have uranium-238 spontaneously decomposing by emitting an alpha particle to form thorium-234. And we see that 234 plus 4 is equal to 238, and 90 plus 2 is equal to 92. Let's write the nuclear equation for the alpha decay of PO216. So we're going to start by writing the nuclear symbol for PO216. So we know that it's PO, and it's 216 is the mass number. And then we have to find it on the periodic table, which is a little, searching around. And it's element number 84. This happens to be polonium, but you can write the equations without knowing what the elements are. So alpha decay, the alpha particle is usually written last. Not sure exactly why, but it is. So there's the symbol for the alpha particle. And now we're filling in blanks here. So we have the atomic number should be A, but it's not. It's Z. Mass number is A. So we're going to find out what A is because we know that 216 must equal A plus 4. So 212. And 84 must equal Z plus 2. So what's Z? 82. That's not hard, huh? To find the element symbol, we're going to look for element 82, which happens to be lead. So for X, we're going to write PB. Any questions? I think it's actually much simpler than balancing chemical equations. So alpha radiation, alpha particles, we use vehicles to help us remember some of the properties of the different types of radiation. So alpha radiation is the 18-wheeler of radioactivity. This is the big semi-truck. It is the biggest, most massive particle emitted by radioactive nuclei. Everything else is smaller. So this is the big guy. It has the highest ionizing power and the lowest penetrating power. So what are those? Ionizing power is the ability of radiation to ionize other molecules or atoms. So this alpha particle comes in and collides with another molecule. It can cause electrons to be spit off, turning that molecule into an ion. Ions have different properties than molecules, and so that can greatly affect the reactivity of that molecule. So if this is something that's going on in your Krebs cycle or whatever in your body, that can cause a big problem, right? So in living organisms, we can get undesirable reactions that result in cells dying or reproducing abnormally. It's really unusual, though, to get a frog with two heads. Right? So that's ionizing power. So this is, in terms of vehicles, this is the semi-truck smashing something, right? A semi-truck would be very good at smashing into a brick wall, right? In terms of penetrating power, this is the ability for radiation to penetrate or go through matter. Alpha particles have low penetrating power. This is like this vehicle is struck in a traffic jam. A semi-truck in a traffic jam, say in downtown New York, is just, that sounds like a miserable place to be, right? You get this big old truck, it's going to be very hard to maneuver through traffic. So there's penetrating power. The alpha particle can smash through walls, but it gets stuck in traffic. It can't go through. Radiation has to penetrate into a cell in order to damage anything inside that living cell. If it can't get through the cell membrane, it really can't hurt the cell. So alpha particles, because of their large size, they have low penetrating power, semi-truck in a traffic jam. They can be stopped by a sheet of paper or even air or clothing, right? So pretty easy to protect yourself against alpha particles. So they are relatively safe outside the body, but if you inhale them or ingest them and get them into your body, then they can be very dangerous because they have high ionizing power. Any questions? Yeah. Ionizing power is the ability of these things to make ions out of molecules. Yeah. Any other questions? So that was alpha decay. Beta decay, a beta particle is eliminated. A beta particle is an electron. So, what's wrong with this sentence? An unstable nucleus emits an electron. There aren't electrons in the nucleus, right? What the heck? So this is where more funny business occurs. A neutron can turn into a proton and an electron. Yeah, what? No, you're messing with my world. Everything's off when you get into the quantum stuff. Everything. So a neutron can break into a proton and an electron, and this is why the electron has a -1 atomic number. Because the sum of the mass numbers here is 1 on both sides, and the sum of the atomic numbers is 0 on both sides. So that part is kind of hard to remember. But beta, I have a question. Why is this mini mart selling sodas in styrofoam cups? Very bad for the environment. With paper straws. Paper straws are nasty. So plastic lid and a styrofoam cup and, oh, good for the environment, paper straws. Electron capture. As the name suggests, this is not an emission, but a capture of an electron. So the nucleus pulls an electron in. Where does the electron come from? From the inner orbital of its electron cloud, so probably the 1s orbital. The particle gets absorbed by the nucleus instead of being emitted. So this is the opposite of beta decay. right? Because in beta decay, a neutron became a proton and an electron, a beta particle that left. Here, we're absorbing an electron that can combine with the proton to form a neutron. So here we have the atomic number decreasing by 1. And we have the electron here as a reactant, not a product. So this is a table summarizing these types of radioactive decay, showing these are the Greek letters, alpha, beta, gamma, and we've got positron emission, electron capture, tells us what happens to the mass number and atomic number, what happens to the number of neutrons per number of protons, and this ratio will become important later, and also gives some examples. So a question that I would have as a student is, what out of this do I need to memorize? Right? Well, you need to know the symbols for these different forms of radiation. So that's the alpha particle. This is a beta particle. That's the gamma ray. That's the positron. And this concept of electron capture. So instead of electron emission, it's electron capture. Yes?
These are just all the naturally occurring radioactive processes.
Yes.
So I'm thinking about like neutrons being, when an atom is split, neutrons flying out, that's not natural.
Well, you could argue whether that's natural or not, but yeah, that's a different thing. So this is a single nucleus just spontaneously emitting particles, right? It hasn't been hit by anything, nothing's been done to it, it just falls apart all by itself. Yeah. And we will talk about fission and fusion, which involves slamming things together. Yeah. And then you should also know relative ionizing power and penetrating power for the different types of radiation. So we'll write some nuclear equations. So here we're going to have 3 nuclear equations that represent the nuclear decay sequence that begins with the alpha decay of uranium-238, followed by the beta decay of the daughter nuclide. So the original thing is called the parent, and what it decays into is called the daughter nuclide. I don't know why it's a daughter and not a son, it just is. And then that daughter nuclide, can have another one, and it can go on and on and on and on. So starting out with uranium-238, 235. And then we need the atomic number for uranium, which is 92. So this is alpha decay. What's the symbol for an alpha particle? Yeah, it's helium-4. Okay, so now we need to figure out what the mass number is. What should the mass number be? 231. And the atomic number should be 90. Is that making sense to everybody? It's one of those things where the math is so simple that sometimes it's hard. So number 90 is, where'd you go? Thorium, TH. So that's the first one. Then this is saying that the thorium-231 will undergo beta decay. So we're going to have another equation here. Thorium 231. And what's the symbol for a beta particle? It's an electron. 0 mass, and it's -1 protons. So the mass number is not going to change. This is 231. But the atomic number will change. What's the new atomic number? 91. And so that is, what is that? I don't remember what that one is. Palladium? That's what I was going to guess, but I think palladium's PD. Protactinium. Protactinium.
Yep.
It's not one you use very often. Okay, so then we have another alpha decay. So the product here, the protactinium 231, is going to undergo alpha decay. It's the alpha particle. And 231 minus 4 is 227. Feel free to use a calculator to do that, because it's really sad, kind of pitiful even, to get an exam problem wrong because you did math in your head wrong. But it's easy to screw up, right? That's a 91, and so this must be 89. 89 is actinium, AC. Any questions? Yes?
Doesn't matter which order you put the products in.
It doesn't matter which order you put the products in, but they usually show the daughter nuclide first, followed by the radioactive particles.
Okay.
But mastering chemistry should accept either order. Any other questions? Write the nuclear equation for the positron emission of sodium-22. So sodium-22, Na-22, it's got 11 protons. What's the symbol for a positron? Yeah, it's the same as an electron, but it's positive. So electron, positron. So then our mass number is going to be the same, but our atomic number is going to go down. So we are going to get neon out of this, neon 22. So any questions about that one? Nuclear equation for electron capture in krypton 76. So krypton 76, again, we go to the periodic table for the atomic number 36. And electron capture means we're adding an electron, right? So that's plus an electron, which is the negative one. And so we're going to end up with bromine. Bromine 76.